Hello again. In this video, we're going to talk about Newton's method. Now, Newton's method is what is known as a numerical method. And it's a numerical method that we can use to approximate the x-intercepts for functions. Now, by now, you're used to finding x-intercepts for functions, but up to this point, you've probably never used numerical methods to find the x-intercepts. You're probably used to using algebraic methods. So for example, if you had a function like this, 2x minus 9, and you wanted to find its x-intercepts, you would just set this function equal to 0 and then solve for x. And of course, you would find that x would equal 9 halves, and that would be the x-intercept. Now, when you go through this process, you're actually solving for x algebraically, using what's known as an analytical method. Unfortunately, there are times when we can't use analytic or algebraic methods to find x-intercepts. So an example would be, let's suppose you had a function that looked like this, e to the minus x, and you wanted to find the x-intercepts. Now, when you set this function equal to 0, you would find that you couldn't solve for the x algebraically. There's just not a way to find x algebraically in this particular case. And so we can't use an analytic method to solve for x. So instead, we're going to use a numerical method to approximate the x-intercepts for this function. Okay, and the method we're going to use is known as Newton's method. Okay, so let me show you how Newton's method works. So suppose we have the graph of some function f of x that looks like this, and we want to try to approximate its x-intercept, which happens to be at this point right here. Okay, using Newton's method. So here's the first step in Newton's method. You make an educated guess as to where you think the x-intercept is, and you call that x sub 0. So let's suppose we guess it to be at this point right here. Okay, and we're going to label that as x sub 0. Now, the next thing you do is you actually plug that into the function, find the ordered pair on the function. Now notice when you do this, you get the point x sub 0, comma, f of x sub 0 out. So that would be the ordered pair that you're at. And what we're going to do is we're going to draw a tangent line at that particular point, which would be this red line. And we're going to try to see where that tangent line intercepts the x-axis at. Okay, and wherever it intercepts the x-axis at, we're going to label that as x sub 1. Now notice that x sub 1 is a better approximation than x sub 0, which was our initial guess. Now to improve the approximation, what you do is you plug x sub 1 into the function and find the ordered pair on the function. And of course, that's going to be at x sub 1, comma, f of x sub 1, right here. And then you draw the tangent line at that point and see where it intercepts the x-axis at. And you label that point x sub 2. And notice again, x sub 2 is a better approximation than x sub 1. Okay, so you continue to do this, and you'll get all these numbers here, sequence of numbers here that begin to approach the actual x-intercept. That's a way we can use, a method we can use to approximate the x-intercept when we can't find it algebraically. Okay, so there's actually a formula that we use when we use Newton's method. So I want to show you where that formula comes from. So let's take our initial guess, x sub 0. We plug that into the function to get this ordered pair here, x sub 0, comma, f of x sub 0, and we draw the tangent line at this point. What we're going to do is we're going to find the equation of that tangent line first. Okay, so to find the equation of this tangent line, notice we do have this point on the line, right? We know this point. We also know the slope of the tangent line. Remember, the slope of the tangent line is the derivative of the function at that evaluated at that particular point. In this case, it's going to be f prime of x sub 0. F prime evaluated at x sub 0. That's going to give you the slope of this tangent line. And so we can use the point slope formula for the equation of a line to actually find the equation of this tangent line. Okay, so we know a point on the line, right? We know this point right here, so I'm going to plug that in. X sub 0 comma f of x sub 0. Then we know the slope of the line, the tangent line. That's just the derivative evaluated at x sub 0. Okay, so that gives us the equation of this tangent line. At this particular point, right, at x sub 0. Now, we want to know where this tangent line intercepts the x-axis, because that's going to give us x sub 1. Okay, and of course to find that, notice the y value at this point would be 0. So if we plug 0 in for y, and then solve for x here, we can find x sub 1. Okay, so I'm going to plug 0 in for y, and then solve for the x value, and whatever it is going to be x sub 1. Okay, so I'm going to plug 0 in for y here. Then we're going to solve for this x value. Now I'm going to go ahead and call that x sub 1, since that's how we're going to label it. Whatever this x value is called or labeled x sub 1. Okay, so to find x sub 1, I guess we would divide by f prime of x sub 0 first. And then we would just add x sub 0 to the other side. Now we have a formula that will help us find x sub 1 given x sub 0. So if I know the previous point, then I can find the next one using this formula. And so in general, x sub n plus 1, the next one, can be found by plugging in the previous one, x sub n, into this little formula. Okay, that's the formula that we can use to continue to find the next x value in Newton's method. So for example, if I know x sub 0, I can plug x sub 0 into here, and that will give me x sub 1. But if I know x sub 1, and I want to find x sub 2, then I would plug x sub 1 in here for these three, and that would give me x sub 2. Okay, so the next video, we're going to go ahead and use this formula and actually find an approximation for the x-intercept for some function using Newton's method. That's where this formula comes from. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.